of Secrets.
Yeah. Yeah. Thank you very much for being here on a Friday afternoon. I hear that you all have fun at this time period, so I'm hoping that I can generate a little fun here for you with my talk. To give you a small bit of background, why I'm talking about the binomial coefficients is that at the moment I'm finishing up a book on them, and that has led me in all kinds of really crazy directions. And I'll tell you a little bit more about the book as I go along. But the subtitle, A Chamber of Secrets, if you've read the Harry Potter series, I have to say it's the worst book in the series, in my opinion. But it's also true that everything that's in that book is really, really important. And so, in some sense, if you want to see the whole rest of the series, you have to read the Chamber of Secrets. And so, in the same sort of way, if you start learning things about binomial coefficients, you'll soon realize that this kind of leads you in ways that spread out all through mathematics. And it turns out that it's also the case that binomial coefficients played a key role in the careers of the originators of the calculus. So I'm hoping, as the talk goes along, to talk a little bit about Newton, and then, in honor of your T-shirt, talk a little bit about Leibniz today. So let me know if I'm loud enough in the back. Jules, I brought my own chalk.
Okay, well we have some.
Yeah, it's good. I'll probably deal all that I have. So, binomial coefficients. I want to look at a binomial. So a binomial is, well, two nomials, right? I'll take this particular case, and the binomial coefficients arise when I raise the binomial to a power. So it's very simple, because if I raise it to the first power, I just get this. If I raise it to the second power, then everybody can do the FOIL method in their sleep and get your 1 plus 2x plus x squared. And if you've got enough patience, of course, after you've fixed your mistakes, you'll get this for the third power. And of course, the coefficients of these accumulate into a table. So if I let n be, say, equal, I'm going to start the table at 0. 1 plus x to the 0 is just 1, right? So my coefficient is 1. 1, I get a coefficient of 1, and 1 here. This is the constant row, and here's the x row. And in 2, I get 1, 2, 1. That's what we just worked out. 3, put this up here. 3, I get 1, 3, 3, 1. And many of you would immediately recognize this as what? As Pascal's triangle, right? And but of course you'll notice I write it sideways, right? Everybody likes to make the Pascal triangle look like this. Don't you crack Pascal? Pascal wrote it like this. Pascal wrote it like this, and so if actually did he? I have Pascal's triangle right here. Oh, he turned this on its side. So it's anyway, it looks a lot like Pascal's triangle. So I want to let's just talk about generating Pascal's triangle. So I want to. There's a rule to generate Pascal's triangle, which everybody probably knows. But I want to consider how this rule comes about. And the rule comes about like this. If I take 1 plus x raised to the n plus 1 power, of course, that's 1 plus x times 1 plus x to the n. I mean, this is fairly obvious, right? Now, let me go a little hog wild with notation here, and let me write this as a summation of the powers. So these numbers here are the binomial coefficients. So I raised this up and I spread it all out, and the coefficients of the x to the k power is n choose k. And let me just notice now, if I write this out here, I'll end up with n choose k to the x plus k, that's 1 times it, plus, well, k equals 0, n choose k to the x to the k plus 1 power when I multiply it by x. Okay? But wait a minute, on the left-hand side here, I have, say, j from 0 up to n plus 1. The binomial coefficients for the n plus 1 row, or column, the n plus 1 column, right? Now, it's a fact, when are two polynomials equal? When are two polynomials equal?
All the coefficients.
When the coefficients are equal, right? When the coefficients are equal. So let's see, so this coefficient here, let's see, well, I have an x to the j over here, right? So that means I'll have one of those, right? Oh, yeah, okay. But over here, let's see, I have to have k plus 1 be equal to j. So k must be j minus 1, right? So I have an entry there. And so I get a rule, right? I get a rule that the next binomial coefficient is determined by these previous ones, right? So taking a look over here, I'm still going to get this 1. The entry here is going to be this one plus this one. Okay, because this is the row for j, and this is the row for n. So here's the n plus 1. So this one is going to be the one to the left of it, and then the one above it. So that gives me this, and of course 6, and 4, and 1. And then 5, I'll get 5, 10, 10, 5, 1, 6, 1, 6, 15, 20, 15, 6, 1. And this beats the hell out of trying to multiply these powers out, right? Right? I mean, this is like crazy, right? If you think about it, you can do this till the cows come home, right? I mean, really. Now, so we can push Pascal's triangle on as far as we want. Let me pause for a second and speak a little bit about calling this Pascal's triangle. In point of fact, this family of numbers showed up around 200 BCE. And the first appearance of these numbers is in a discussion by an Indian, essentially an Indian poet who was analyzing the beats of strong, weak pulses in a line of Indian poetry. And so the question of how many lines of poetry do you have that have 10 beats in it, 5 of which are strong and 5 of which are weak? Well, it depends on where you put the strong ones, right? But it's strong, weak, it's not ordered in any case. And so these numbers turn out to be exactly the answers to those questions. So that shows up in the discussions of Sanskrit poesy by Pingala. Shu Shijia in China referred to a work that comes from the 11th century that has this so-called Pascal's triangle in it. And Omar Khayyam, the famous poet, the 11th century poet of the Arabic world, also had researchers on this Pascal triangle in his time. So all of this is before the 17th century Blaise Pascal writes his book. Now, yes, these are the binomial coefficients, but this is not how you say this symbol. It's not how you say the symbol. So this symbol is pronounced in the following way. It's called N choose K. So let me tell you why this is called N choose K. So the binomial that I take the power of can be any binomial. And so I'd like to take the binomial called y plus n, and this is for yes or no. Yes or no. So if I take and I write this out as, well, yes or no times yes or no, yes or no. Okay. When I pick out something that has, say, k yeses, and, well, it'll have n minus k no's, right? What I'm doing to assemble the coefficient in front of here is asking the question, how many ways can I pick, well, a first thing? Do I pick the second thing? Do I pick the third thing? Every time I do a yes, I put a yes here, and then and the rest of the time, of course, I pick no, because I have to pick yes or no, yes or no, yes or no. And so, so the number that appears in front of this, which of course is this number here, this is going to be equal to the number of subsets of 1, 2, up to n with k elements. Because, well, a subset's not ordered, right? And so all I really want to know is which places did I pick yes. So I'm going to get like y to the k and an n to the n minus k. And I just want to know how many ways that happens. Well, that's this number, but of course we just worked out what those numbers are. Right? Worked out what those numbers are. So this is the origin of the notation, or I'm sorry, the pronunciation of the notation, and it corresponds to this formulation of how we're doing this counting. Now, in fact, Pascal was really interested in this formulation and this meaning of the numbers, because what Pascal was trying to analyze in his book were games of chance. And so he wanted to know, well, how many ways certain things happen. So an important calculation involved in this, of course, is this number here, 52 choose 5. Let's see. Well, we'll figure out what number this is. This will be the number of five-card poker hands, right? So, I mean, this is an important number to know the actual value of and how they analyze
A lot
this.
of probability kids in here, we do this.
Oh yeah, you bet, you bet.
Call it CN.
Yeah, yeah, I know. So,
Yeah.
so actually,
Yeah.
let's see, what do you call it?
For N take K, we watch CN.
Where'd you put
The N goes to the left.
to the
Lower, yeah, lower left.
lower left?
Take J. Yeah.
Yeah, see.
That's
now-
okay. They follow.
No, I'm just putting it up here because I think this is like, this would drive me totally nuts, trying to figure out who's on the bottom and who's on the
Yeah.
top. And I mean, this piece of notation,
Hard time.
tell
Yeah.
it to hit the road.
Yeah.
You know, these are much clearer.
Yes.
These are
Beautiful.
much clearer. Just putting that out there. These were introduced, by the way, in the early 19th century by von Emminghaus, and Euler had a similar kind of expression of this. Well, I'm a little put out by the following problem, which is if I want to know 52 choose 5, do I have to do 52 rows of the Pascal triangle in order to get there? Too much work. Mathematicians are lazy. Mathematicians are lazy. Much mathematics is generated by trying to think of a way to understand something so you don't have to do any work. Okay. One thing, if you do a lot of work, you'll make a mistake en route, and therefore you'll end up with the wrong answer, right? So you should do things with the least amount of work so that, well, you can check it, right? So let me. How many folks here actually have calculus? Most everybody?
Many of them.
Many of them.
Calculus,
I think many
or
of you.
they've had statistics.
Yeah.
A lot of these people are stats.
I need just one simple fact, which is that derivatives are linear, right? Derivative of a sum is the sum of the derivatives, and etc. And let's see, I think I need that the derivative of x to the k is k x to the k minus 1. Yeah. Okay, everybody good with that? Yeah. So let me just point out the following. Well, I can calculate the derivative of this by the chain rule, I guess. Everybody should know the chain rule, right? This is n times 1 plus x to the n minus 1. But now I want to remember the binomial expansions. So let me just rewrite this as, well, this is n times k equals 0 up to n minus 1. N minus 1 choose k, x to the k, right? Okay, that's on the right-hand side. On the left-hand side, I'm taking the derivative of summation L equals 0 up to n, and choose L, x to the L. Right? Okay, so now I have two polynomials floating around. On the left-hand side, because of the linearity here, I'm going to get L equal 1 up to n. And then I take the derivative of this, which is L x to the L minus 1, right? And so this is, on the other hand, going to be equal to this k equals 0 to n minus 1, n minus n times n minus 1, choose k, x to the k. So now we have to set equal things that have the same monomial, right? So we're going to set the coefficients equal. And let's see, I think that's going to give me L, and choose L, so that's the coefficient of this to the L minus 1 equals n minus 1, here L minus 1. So the L minus 1 will be over here, so I guess that has to be here. So that gives me that. So that gives me a conclusion. I have an identity, right? I have an identity. And in particular, I could write this as n choose L is n over L, n minus 1 over L minus 1. Okay. Oh, wait a minute. This means that this is n minus 1 over L minus 1, n minus 2 over L minus 2, right? Okay, so I can start pulling these things out. And, well, I can keep doing this till the cows come home. And when do the cows come home? Let's see. It's when I get to 1 in the bottom. And on the top, I'll get to n minus L plus 1. That is, there are L. When I get to 1 here, I stop because the next thing, because I've gotten to this row here. So. Or maybe I go to 0. I don't know. Either way, this is where I stop. I have L things. So this is let's see, n times n minus 1 down to n minus L plus 1 over L factorial. L factorial. And well, okay. There's a formula. There's a formula that picks out the binomial coefficient way over there, without having to calculate all of the entries in the Pascal triangle in order to get there. So 52 choose 5 is pretty easy, right? 52, 51, 50, 49, 48 divided by 5, 4, 3, 2, 1. Let's see, so I can take this and that gets rid of that. And then if I do this, then give me a 12 over here. And then 3 goes into 51. 17? 17, okay. So this is 52 times 17 times 5 times 49 times 12, which we all know is equal to 2,598,960, of course. So there we go. So that tells you that you can actually calculate these things when you want to. And I kind of like this simple derivative derivation of this that you can get pretty much almost for free once you know just a little bit of calculus. And it gives rise to this beautiful thing here. Another way to look at this, what's the right way to look at this? Let's see. This is the number of ways to pick a committee with L people in it, right? Out of N people to start with. So this is the number of committees, and of course you have to pick one of the persons in the committee to be the chair of the committee, right? Okay, so here I'm picking the committee and then I pick the chair. And once I pick the committee, of course I have L choices for the chair, so that's why I multiply those. On this side, if I pick the chair first, and then I pick the rest of the committee. Of course, once I pick the chair, I only have n minus 1 people to choose from. And I only need L minus 1 many people left to fill out the committee. So this is how I pick a committee with L people together with one of those people being the chair. And this is how I pick a committee of L people with one of those people being the chair. So these are equal, right? So one of the points that this makes is identities like this among binomial coefficients are in fact have as their source not just well, a little bit of calculus or some algebraic calculation, but also these combinatorial arguments that allow you to have access to why these things are equal. And I'll come back to this point later about the fact that there are many approaches to this set of ideas. Stop me if there are any questions, by the way. Is everybody good? Everybody good? Okay. Well, here's what I want to do with this. One of the reasons, of course, that everybody in the room chooses to study mathematics is because of the ability in mathematics to pose the question, what if? What if? In mathematics, you could say, you know, I got these things, I know how they, I can play around with them, I know what to do with them, but what if this is true? So here's a what if that, that I want to introduce. First of all, I want you to see the Pascal triangle now. It all goes down here, but notice all down here, really below here, is just a whole gigantic sea of zeros, right? These are all zeros in here. So if you fill that out, I mean, first of all, it fills out the columns going down, but it also, I mean, in some sense, what it's saying is that when I take things to a power, I get a polynomial. And polynomials have a highest degree, right? So that's what that's saying. But what I'd like to do is do this. What if I had a column like this? Well, I know what Pascal's relation is, right? So I know, well, I know I have to have a 1 here because everybody is a 1, right? But now, this plus this has to equal 0, right? So this must be minus 1, right? And then this plus this has to equal 0, so this must be 1. And then this plus this has to add up to 0, so this must be minus 1. And I think the pattern is apparent, right? That I'm going to just be alternating here. 1 minus 1, 1 minus 1. But notice, this is going to go on forever, right? This is going to go on forever. This was fun. Let's do it again. Let's see. Well, I have to have a 1 here, right? So this plus this has to be minus 1, so this must be minus 2, right? And this must be 3. This be minus 4. This is 5. Minus 6. 7, right? And then it starts to get interesting, I think, over here, right? I have a minus 3 here, but then I need a 6 here. And then this would be a minus 10. This has to be a 15. This would be a minus 21. This must be a 28, right? And these go on down like this. Well, okay, so I'm doing this from a what-if point of view. Does this hold any water, is the question, right? Well, one of the things which I hope you learned someplace or another is a thing called the geometric series. And the geometric series is takes the following form, that if I add up all the powers from the 0th power on, I get 1 minus x. It's very easy to prove this, by the way. If I take and well, I'll do it this way. I take this and multiply it by 1 minus x. Let's see, this gives me 1, right? And now notice, this plus this is 0. 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 So you get this nice pattern that goes on, and so those are equal to each other. So that tells me then, of course, that 1 over 1 minus x is equal to this. Right? Well, that would mean then that 1 over 1 plus x, well, let's see, that's 1 over 1 minus x, right? That's going to be equal to, I put minus x into this, and I get here 1 minus x plus x squared minus x cubed plus x to the 4th minus x to the 5th plus plus, right? Or in other words, I'm getting an alternating series of plus minus 1. Check it out. The coefficients are right there, right? Now I was making this up with the Pascal triangle thing, right? But look out, it works, right? It works. How cool is that, right? So we must be on the right track. We must be on the right track. But I don't, we don't want to get too cocky about this. So let's take. How about if we took this and multiplied it by itself? Right? So this is 1 over 1 minus x. So if I take 1 over 1 minus x squared, this should give me the minus 2 column, right? This give me the minus 2 column. So let's check it out. Looks good for the 1 part, obviously. So now let's see, the things with x, I get 1 times x, and 1 times x, I get minus 2x. Now if I'm going to do the x squared part, let's see, I got a 1, 1 plus 1 plus 1, right? So I get 3 x squared. And now the x cubed part, I'll get minus 1, minus 1, minus 1, minus 4, okay. And the x to the 4th part, while it's here, let's see, I get 1, 2, 3, 4, 5. I get 5 of them, right?
Love the way you're doing that. Love the way you're multiplying that.
Right?
That would help us the other day, Simone, in the calculus problem.
Oh, good, good. Not bad, huh? Not bad. We got the right answer, right? We got the right answer. So I'm not going to do the cube for you, but because I think you get my idea here. This is working out nicely, right? So does it work? Does it work from the other point of view, which is that? I mean, I got a formula here that works. It should be the case that I'm going to get the right answer for that. So how about if I put in minus 1, choose k, right? Minus 1, choose k. So according to formula, I guess I take, this is divided by k factorial. I take minus 1, minus 1, minus 1, which is minus 2, minus 3, 1 down to minus 1 plus, minus 1 minus k plus 1, right? Which in fact is what? Minus k, right? Minus k. So, I mean, this is real, minus 1, minus 2, minus 3 on up to minus k is just a bunch of minuses times 1 times 2 times 3. So, on the top here, I have k minuses, and then I also have k factorial, divided by k factorial. So it's equal to minus 1 to the k. That is, it's just the sign, right? So here's minus 1 to the 0, minus 1 to the 1, minus 1 to the 2, minus 1 to the... So it's just, so here's the alternating thing going for us here. And so this picks it out, right, right immediately, right? And, well, how about minus 2 choose k? What the hell, which is, check it out, right? This is minus 2, minus 3, 1 down to minus 2, minus k plus 1, which is minus k minus 1, right? Divided by k factorial. And let's see, if I take out the k negative 1s, I end up with k minus 1, k minus 2, 1 down to 2, 1 down to 2, divided by k factorial. Nope, no, I do not. I'm sorry. Take that back. I started out with k plus 1, then I have k, then I have k minus 1, 1 down to 2. There we go. And you won't mind if I multiply this by 1, right? Okay. So now I have k factorial. So this is going to be equal to minus 1 to the k times k plus 1. And sure enough, that's exactly what I get here, right? This is 1, so this is 2, this is 2, this is 3, this is 3, this is 4, and it's 1 gives me odd, 2 gives me even, 3 gives me odd, 4 gives me even. Right? So plus minus, so it's exactly correct, right? So this formula, this closed formula which we got, is potent, right? This formula is potent, and so why not? Let's go a little bit crazy with that, right? Okay, so well, let me pause for a moment and figure out. I think everybody is sitting out there going, look at these numbers here. Look at these numbers here. Don't they look just like these numbers here? Except for the plus minus, right? Except for the plus minus. Is there something going on there? Is there something going on there? That is, these things here correspond to rows over here on the positive side. I mean, it's pretty hard to ignore that those two things are available, right?
Is there any connection there with the derivative?
Anything that you can find a
And that thing
connection
here,
with, you can make be connected by the derivative. Yes, so that's probably a fact.
I
Yeah.
did see that.
Yeah. Well, let's just do this. Minus n, choose k. Well, we have the formula, so let's beat up on the formula. Minus n minus 1, 1 down to minus n minus k plus 1 divided by k factorial. Okay. Let's see. If I fished out all the minuses, I would have that many minuses. And then this would become what? N plus k minus 1. And then the next thing up would be n minus k, n plus k minus 2, 1 down to n plus 1, down to n divided by k factorial. And they're exactly k entries on the top, and so this will be equal to minus 1 to the k, n plus k minus 1, choose k. So the negative one, well, I could move this to the other side if you like, and that would take away the minuses here, and it would leave me with this expression here. Well, that's exactly this line here, right? It's exactly this line here. So sure enough, these are related. Now, I talked about this being about choosing things. So let me show you, in fact, that these numbers are about choosing things. So I'm going to make another binomial, or another set of choices. So I want to choose. I want to take 1 over 1 minus y raised to the nth power, because, and I call it y because I want y to be yes. But I'm going to let 1 be no, because I want 1 to act like 1, okay? So this is equal to, let's see, 1 plus y squared plus y cubed plus 1 plus y plus y squared plus. dot 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 1 plus y plus y squared. Okay, so now I have n things, right? I have n things. So here, no, or yes to 2 things, or yes to 3 things, or yes to 4 things. So what do I mean by 4 things? Yes, pick the first thing. Oh, yes, pick 2 of the first thing. Yes, pick 3 of the first thing. Pick 4 of the first thing, whatever you like, right? Keep doing that. So y to the k corresponds to, well, let's not make it k, let's make it m. Choose 1 m times. Okay. And over here, choose 2 however many times. Choose 3 however many times, right? Well, this is going to multiply out, and it's going to give me a series. In fact, it's going to give me the series given with these coefficients. But wait, I think I'm using a minus here. I'm using a minus here, and that's for the plus, and that minus is going to take the and put a minus here. So I'm just going to get this number here. Just going to get this number here. And so this is going to equal the summation of k equals 0 to infinity, the number of ways to choose k things from n things with repetition. Right? With repetition, because the exponent here says, oh, I picked 1 3 times. 1 3 times. Of course, now I only have k minus 3 things to distribute across here, but that's okay. And then it'll be this times y to the k. But of course, this is equal to summation k equals 0 to infinity n plus k minus 1 choose k y to the k. So that establishes then that the number of ways to pick k things from n things with repetition is this number here. And of course, this is a number you can calculate, right? It's a number you can calculate. So that's an expression of that. Let me, because of the new T-shirt, I want to talk a little bit about Leibniz today. And for Leibniz, one of the most life-changing moments for Leibniz was a discussion that he had with Huygens around no, it can't be in the 16s, I think. Wait, it is around 1672. Around 1672, where Huygens asked him to solve the following problem. What is the sum? What is the sum? 1 plus 1/3 plus 1/6 plus 1/10 plus 1/15 plus. Now, where did I get these numbers? Well, I guess I got them here, right? But actually, I'm getting them here. These are the numbers, and so these numbers are 1 over. What is it? 3 choose 2 plus 1 over 4 choose 2 plus 1 over 5 choose 2 1 over 6 choose 2, etc., etc., etc. And actually, these numbers here, 3, 6, 10, 15, are these numbers here. 1, 3, 6, 10, 15. These are the triangular numbers, the numbers that form an equilateral triangle like that when you make them out of stones, right? Okay, so Huygens said, can you sum the infinite sum of the reciprocals of the triangular numbers? So these are the numbers that he looked at. Well, it turns out that he was up to this. He was up to this, and so let me tell you how he solved this problem. He made the following observation. First of all, I could rewrite these numbers as this is 1 plus 2 over 3 times 2 plus 2 over 4 times 3 is 2 over 5 times 2. I'm sorry, 5 times 4 is 2 over 6 times 5 plus plus plus, because of the that explicit formula which we have for the binomial coefficients. So I have a 2 in the denominator and the numerator like that. And so this, of course, is equal to 2 times 1 over 3 times 2 is really a half minus a third, right? If I take a half minus a third, I get 1 over 3 times 2. If I take a third minus a fourth, I get 1 over 4 times 3. If I take a fourth minus a fifth, I get 1 over 5 times 4. And so on, right? And this is exactly a beautiful situation, because these cancel, these cancel, these cancel, these cancel, and in fact, they all cancel each other. Well, except for the 1/2, right, in the front, which times 2 gives me 1 plus 1, tells me that this is exactly equal to 2. Exactly equal to 2. So Leibniz realized this, and in fact, he said, well, what if I can do better than that? So take the Pascal triangle and write, instead of the Pascal things, write their reciprocals. Let's see, this is 1, 4th, 1, 5th. Maybe I'll do one more here. 1/6. Okay. So this is Leibniz's harmonic triangle. Okay, which he talked about, and well, if you add these up, you get 2. Actually, you get 2 over 1, as is how he would like to put it. And so let me leave you with the following puzzle, okay? Let's change this. And let's see, I need to get this started. So I'm going to take K plus 1 choose K, K plus 2 choose K, K plus 3 choose K, K plus 4 choose K, etc., etc., etc. So in other words, when K is equal to 3, I'm going to get this sum here, okay, is equal to 4, and get this sum, et cetera, et cetera, et cetera. Okay. So what is the sum of these numbers here? What's the sum of these numbers? And, well, I'll tell you what the answer is, and then I'll let you figure out how to get it by using these formulas. The following pattern shows up. And actually, if you really want to extend this further, I guess you should put that there, which is okay, right? Since the harmonic series diverges, right? And so, so here's a beautiful pattern. Here's a beautiful pattern, and it's actually so. I'll leave that as a puzzle to you, a puzzle whose answer was given by Leibniz in the 1670s. It's true that Leibniz discovered these kind of telescoping sum methods to solve values of infinite series. And if you start to think about it carefully, taking the infinite sums that telescope like that and using that to analyze the geometry of an integral leads you, with the mean value theorem, to a proof of the fundamental theorem of the calculus. And so Leibniz's solving this problem here, this first problem, led him in a direction that in fact pointed him to the calculus, which is a pretty amazing fact. There's a piece of luck that Huygens posed that problem, and he was able to solve it in such a quick way. Otherwise, he might not have come upon the telescoping methods and arrived at the calculus the way he did. I'm out of time, but I'll just point out that you could put a half here, and maybe a minus a half, and of course 3 halves. Oh, better put it in the right place. 3 halves here, 5 halves here, and fill in these numbers here. Well, let's see. This better be 1. This better be a half. This will turn out to be minus 3/8, and we'll get numbers that go down forever like this. The person who did this first, was a young man in 1665, and if you, I don't know if you can see this, but there's a table in here, and this table has the column for minus a half, and the column for a half, column for 3 halves and 5 halves, and on and on and on. And this of course is Isaac Newton. This is Isaac Newton during the miraculous year that he spent away from Cambridge, avoiding the plague. And the first thing he was thinking about was the binomial theorem for exponents that aren't equal to a whole number. And so he did this first part of the experiment to fill in the negative numbers, and he used this column here to do integrals that gave logarithms. And in fact, his logarithm numbers were carried out many, many places, and he was able to observe that they were better than the numbers in Mercator's logarithm tables. And then he decided to try 1/2 and minus 1/2, and using these numbers and these numbers came up with a calculation of pi that was completely amazing. And in fact, I've tested his calculation against some other methods, and it's a very rapidly converging infinite series that gives pi very, very well. So the experiment in his mind is a what-if experiment, filling in these numbers and then seeing what he got. And in fact, he got an infinite series that gave the right answers for pi and such. And what he needed to fill in was just exactly how to do this for things other than the circle. That is, to fill in the rest of the differential and integral calculus, which of course he did, and for which we are all grateful to his thing. Binomial coefficients then played a role both for Huygens, for Leibniz, and for Newton in their what directed them to the invention of the calculus. So, as a place where there are many secrets hidden, binomial coefficients are a rather deep and rich place to look. And so, I think I'll stop with that then.